So I know why all of you are here. You're here to listen to me make funny noises with my computer. But before I dive into anything audio-related, I want to present a little bit of an analogy first. So let's say you are trying to model a traffic light signal, and you just want to emulate that signal turning yellow, then turning red, then it waits a bit, then it turns yellow and green again. Maybe you're I don't know, a traffic engineer or something, and you want to be able to model the flow of traffic, and for that purposes, you need a simulated traffic light. So one approach that I might take, let's say I'm fresh out of school, and I think, oh, I know, I'll just create a variable for the traffic light state. So there I go, I'm feeling all clever. I create myself a lovely enum here with red, yellow, and green as separate states, and then I assign, for instance, the green state to a traffic light variable. And sure, this works, but it's not great because that traffic light is just going to stay green and green and green, and it's never going to change until you reassign it. And you could, for example, throw in a loop, add sleep statements, and you have a changing traffic light, but it's not great. You don't have a lot of control over that. And if you want to change anything at all, you have to change the entire way that this workflow works. So one way that you might do this instead is you might implement a signal workflow, where instead you would, for example, there we go. For instance, you could do something a little bit more complicated like this, where you decide to use a generator function. And for those that haven't used generators before, it's sort of like a regular function, except rather than returning a single value all at once, you can return as many values as you want forever by using the yield keyword, and it does that by using an iterator. So over here, for instance, this here is the generator function. It's taking in 3 parameters for the duration of a red, yellow, and green traffic light. And then afterwards, in a loop, it's just going to yield those values in turn. It's going to go red for however long you specify, then yellow, then green, then yellow again, and so on. And this is a better approach because now we've separated the logic. We've got one part where we define how the traffic light behaves, and another part where we actually are able to run this. So if I was to run this here, you can see that we now have control at the business end of things, at the simulation end. We can say, for instance, sleep 1 second in between each tick. And we have full control over that during the simulation. We can store the state of the traffic light. If we wanted to save the history of the past 10 seconds, for example, we can do that using just a list of length 10. And sure, this is cool and all, but what's the point of doing this? Well, this here allows us to use stream processing, where rather than waiting for some sort of computation to finish and you can do something afterwards, you have the ability now to do some sort of action right as the data is coming in. That sort of mock example of a traffic light could be a data source from absolutely anywhere. And what we can do with stream processing is react to real live world data, and this is used everywhere all the time. For example, finance firms absolutely love this because they get to look at stock market data and get to be the first to react to any price changes. This is used by meteorologists to predict the weather so that they can continually give you live updates about what they think will happen in the next hour, in the next day, in the next week, whether it will rain or not. It's used by roboticists, where they will be constantly reading live sensor data. For instance, let's say you're making a self-driving car. There will be dozens of sensors all over that car, and you need to react to things instantaneously. It's no use if the car's already crashed, and afterwards, in a post-mortem, you go, ah, yes, the car should have turned left over there. It's used by statisticians because by processing data as it comes in, that can be much faster and much more time efficient than waiting until you have gigabytes or terabytes of data piled up. Then you run your Python script or a Jupyter notebook over that, and then you're stuck there waiting for hours, days, weeks, however long it takes to crunch through that. And lastly, audio engineers. Possibly indirectly, but this concept of stream processing is used all the time for processing all sorts of sound, for hooking up instruments. This microphone that I'm using now, it's all happening in real time. And Sure, maybe the average audio engineer isn't thinking, ah, yes, I'm using stream processing, as in plug this microphone in. But you use it for synthesizers, where you take some data about some parameters or what note you're pressing, and you turn that into an audio signal. It's used in effects. So, for instance, you might have a looping pedal, or you might have reverb or delay or distortion effect used in a live band, which takes in some audio, mangles it or changes it in some way, and then outputs some more audio, which maybe sounds better or worse. Then you have audio interfaces, which is how you get computers to talk to instruments. So if I have an electric guitar and I want to record it, I can't just plug that guitar straight into a USB port. I need something in between which speaks the language of both the guitar and the computer. So that's constantly passing data and audio back and forth through it, and doing a lot of conversion, amplification to make sure that the levels of everything is okay, and all sorts of other clever tricks under the hood, which I am by far not experienced with, and the companies like to keep quite secret and stick fancy names on because it's what gets them to sell their products. And the list goes on. We're talking all sorts of instruments, microphones, mixers, recorders, speakers. All of them are handling this audio in real time. And this, at first, might not seem too difficult to do. Just write a program which has a loop in it, or waits for new data to come in. But if you take a peek under the hood, things do get a little bit more complicated than that. So let's talk about the headphone jack. Everyone's used a headphone jack. It's also known as the audio jack, phone connectors, aux ports. It's what you use to plug in headphones into your computer, or that port on the bottom of your phone, which everyone is now removing and charging you extra for a dongle. Headphone jacks are great. They're also probably the simplest connector to ever exist, excluding the power cable. And that is, they have pretty much zero latency. That is, the only latency is the speed that it takes the electricity to get through the cable. That's it. And they have absolutely no protocol. It's just raw voltage being sent right through the cable. Again, sort of. If you send 100 volts through a cable, you're probably going to end up breaking all of your equipment. But as long as you keep things under reasonable thresholds and you respect the voltage limits of whatever device you're using, any raw data you send in is just raw data that comes out. You don't have to deal with USB protocols. And it has an infinite resolution. Again, sort of. The resolution is just however fine-grained your measuring instruments are. What's being sent through is just a raw voltage signal. There's no set frequency for it. Just whatever value goes in is whatever value comes out. You can measure it using an oscilloscope from your school physics labs, for instance. And there is one massive disadvantage of using analog audio for everything, though, because by this point you might be thinking, if these are so great, why don't we use them for absolutely everything? That being that they can get a bit monstrous to use. This is an example of a modular synthesizer for making electronic music. And there are lots of hobbyists which love this kind of thing, but you're not going to fit this in your pocket. You're not going to be able to take this to your band gigs or wherever you want to take this. And it's really, really complicated to use, and will probably take the same amount of power as a family of 4 living in a suburb. So as an alternative, most of the music production we do now is digital. And going from analog to digital is actually surprisingly intricate. It takes a lot of maths, which is probably well above my knowledge grade to talk about, but we need to turn an analog signal, like we've got at the top, into a digital signal, which is shown in Audacity on the bottom there. We need a way to be able to read those values and get a computer to understand them, because computers don't deal well with infinite resolution or infinite data. So the way that we can go about this is we take that analog signal, which is sort of like an SVG. It's sort of like vector graphics in that you can just take a bunch of samples of that and slice it up into a bunch of small pieces, and then store the values at each piece. So on that bottom graphic there, you might be able to see a bunch of dots there. Those dots are individual discrete samples of a wave. So in order to convert that, we now have to ask ourselves the question, how rapidly do we want to take those samples? If we were to convert from a vector image to a bitmap image, that's going to have a resolution. So what's the equivalent for audio? Well, we have what's called sample rate, where we ask ourselves, for each second of audio, how many pieces do we want to slice that into, and how many samples will we then be storing? And the higher the sample rate, the higher the resolution. So as you can see here, if we were to take just this simple sine wave, if you sample 10 points, you get a pretty good representation of the sine wave. If you only sample 2 points, you can barely tell what's going on. You have no way of telling whether that was originally a sine wave, or a sawtooth wave, or something else. So the trade-off there is just the more data points you sample, the bigger the file size, the more it takes to process, but the finer the quality, the more information you store. And the less you sample, the less information you store. Except there's a bit of a catch in that some very, very clever people went and developed something called the Nyquist-Shannon theorem, which says that if you have twice as many sample points as the highest frequency in a wave, you are able to reconstruct that original wave perfectly. Which is a bit of an odd concept to think about at first, because that's like saying you take a vector graphic, you turn it into pixels, and then you can turn those pixels losslessly back into the original SVG file, which isn't normally possible with images, but it is with audio. You can do all sorts of maths involving Fourier transforms to reconstruct the original wave, and you know exactly what you had previously. And since the upper limit of human hearing is roughly 20 kilohertz, so 20,000 samples per second, double that would be 40 kilohertz. So the standard sample rate for most audio that you listen to is just a bit above that, just as a little insurance. The standard is 44.1 kilohertz, which means that when you play audio through a computer, it is moving the speaker position roughly 44,100 times a second, which is a lot compared to other media formats. For instance, this projector here is displaying at 60 hertz. It's updating the screen 60 times a second. My display on my laptop is 165, which is 165 updates per second. 44.1 kilohertz is still going to be 2 orders of magnitude higher than that. And computers don't really like that. Oh, look, I've got a lovely to-do message there. Isn't that wonderful? Must have pulled the wrong version of the presentation. Oh, well. Happens. So the solution to this is buffer size, because computers don't really like it when you tell the computer to run something 44,100 times a second. Python will manage it fine, except the moment you decide to do something else on your computer, say you launch an app, that will cause a tiny bit of latency. And even if that causes just 1 millisecond of latency, even if it updates 1 millisecond late, you'll hear that as a really ugly pop on your computer. And your music will be all nasty and distorted. So the solution is something called buffering, where rather than saying, OK, play each sample one by one, move the speaker one position at a time, we allocate it into chunks. So for instance, we can have a sample size of 128, which means that we are going to have a list of length 128, and then we are going to render out all 128 samples, decide where the speaker has to go for them, and then give all of that to the speaker all at once. The speaker then has a digital audio converter, which takes that information, parses through it, figures out where to move the speaker, and then all's good. You get to hear your music without any ugly distortion. However, it does mean that we have a little bit more work to do on the programming side of things. So to present an example of that, let's say we want to make a sine wave. Finally, I'm tying this back to the software in question. This is about Synchrotron, which is a program that allows you to construct your own synthesizers and process audio just by writing Python. And I'm going to create a sine node, a node just being a single module which takes in some data in and puts some data out. You can think of it as being equivalent to a single instrument or being a single effects pedal. So what I'm going to do is I'm going to define an input and an output. I've got frequency in and I've got an output that's just named out. Because if you want to produce a sine wave, you need to know the frequency of that sine wave. You need to know how fast it's going to oscillate. And then afterwards, you want to be able to actually send that sine wave somewhere, for instance, a speaker, so you can hear it. And I'm going to create this render function here, which takes in some rendering context. This has information such as how big do we want this buffer to actually be? Do we want a 128 buffer, which would be quite small and you'd have almost no latency, or do you want a massive buffer? Let's say we had a buffer of 44,100 length. In that case, the buffer would be an entire second. So all playback would be delayed by 1 second. However, it does mean that if the computer's a bit slow, it has that leniency of 1 second to catch up. So as long as it gets the audio done within 1 second, you're all good. And firstly, I'm just going to use NumPy. I'm going to create an empty array with the length of the buffer size. And I'm going to use floating point values between -1 and 1. And I'm going to write this to that stream output. And this, so far, isn't very interesting. It's just going to produce complete silence. It's an empty array. It's writing an empty array to the output. You're not going to hear anything. So let's now actually produce that sine wave. So I'm going to add a constructor. This is just standard Python stuff. The node takes 2 parameters. One of them is this Synchrotron parameter, which is a global object that holds the state of the entire program, and the other being the name of the node, since each node needs a unique ID for the program to keep track of. Those are just being passed into the constructor, which isn't particularly interesting, but we are going to create this field here. We're going to say, let's create a phase variable and set it to just be 0 at first. So then what we can do is inside of this render function, we can say it's time to actually produce a signal. We're going to read in the frequency from that input. So for instance, that could be 10 hertz, so the speaker will oscillate 10 times a second, or it could be 440 hertz, the speaker will oscillate 440 times a second. And we're going to say, for each sample within that buffer, we are going to take the sine of the phase and write it to that buffer. So we're computing just this buffer at the moment. This isn't being written directly to the speaker, because that's where you get all sorts of nasty, garbled audio. All we're doing is we're going to compute the sine of this one sample, and then we're going to increment the phase. So we're increasing the phase by 2 pi, multiplied by the input frequency and divided by the sample rate. So this is just saying, if you were to imagine an angle that was revolving within a circle, 2 pi would be a full revolution. Therefore, 1 hertz would need a full revolution. If you increase the frequency, you want to revolve more times. And if you have a higher sample rate, you have a smaller jump between each sample. Therefore, you need to slice it up into smaller parts. And altogether, this will create a sine wave that will be output to that stream output. But let's see that in action now. So this here is Synchrotron now running. And I am going to use this console over here to say, let's create that sine node that we just demonstrated there. And here it is. But by itself, it's not actually doing anything. It needs an input and an output. So I'm going to say, let's input a value of 440, and let's output to a playback node, which is going to run it through the speaker. So if I was to take that 440, wire it into the sine node, then take that sine node and wire it into playback, you get a sine wave, which is nice, cool, but it's not that exciting. We can do more with this. That input there, that 440, isn't just a static 440. That is still a stream. So that is the value 440 being passed into the sine node 44,100 times a second. It doesn't have to be static. We can make that, for instance, the output of another sine node. And what we would want here is, right, let's see, there we go. What we could say is make this sine node oscillate. Currently, it's going between -1 and 1. Let's make it go between -440 and 440. So to do that, we need to multiply the amplitude of it by 440. And that sine node there can have a frequency of, for instance, 1. So now, lots of dragging and dropping. But I should be able to take that sine node here, multiply it by 440, and then make that the new frequency. And now you can hear it oscillate. It goes woo, 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 and gets very annoying very quickly. But this is a simple and very annoying example of something called frequency modulation. This is the same thing that, for instance, your FM radio does in order to communicate all sorts of information wirelessly over radio. It's also used very frequently in music and sound design. But this can be built up potentially limitlessly. Your only limit being how fast your computer can actually run this. Eventually, you'll have such a big graph that it'll be too slow to actually compute. It will not finish rendering those 128 samples in time, and then you'll hear a tiny bit of silence every 128 samples, which you'll hear as distortion, which sounds absolutely nasty. You might have heard it before if your computer's lagging, and then all the audio goes all glitchy. So the only limitation is now just how much compute power you have. And this system doesn't have to only deal with static values that are created in the computer. You can also take in data from externally. For instance, I've got myself a MIDI keyboard over here. And if I was to, hopefully, what I should be able to do is create a oh, let's see, where is, sorry. Oh, right, thank you. There we go. So then new sine node, new playback node. What I'm doing here is I am saying, let's read whatever that keyboard is transmitting on port 1, and then turn that MIDI information into a frequency, which is what this monophonic render node here is doing. After that, take that frequency, pipe it into that sine node that we made earlier, and then play it out to the left and right speaker channels. And hopefully, there we go. Now you can use this as an instrument. And this is exactly what is happening when you play a synthesizer or play a keyboard into a digital audio workstation for music production. For instance, FL Studio, Bitwig, LMMS, there's loads of them, and different music producers tend to get into fights over which one's better, just like with Linux distros. But that there is how, in a pretty simplified form, but that is how synthesizers and audio processing on a computer works. Normally, this would be implemented using frameworks like the Juice framework, which is C++. As far as I'm aware, I think this might be the first time this has been done entirely in Python, unless you count the NumPy stuff, but you can also just use Python list if you wanted to. And this can be not as scalable as implementing this in a compiled faster language, but one advantage of doing this in Python, the language we all know and love, is that you can do a lot of stuff with dynamically loading in modules. So I don't have to restart the server if I was to program in a new node, for instance. This opens up a lot for live coding and for interactive development. You don't have to rebuild and recompile everything. You don't even have to restart the server. You can do some really cursed things using importlib. And there you have it. That is Synchrotron. You are more than welcome to try it out for yourself. I will warn you, the documentation is currently incredibly limited, but if you do reach out, genuinely, I'm always happy to answer questions or help out in whatever way, shape, or form. Thank you so much.
Absolutely fantastic. Good work. Well, you have a question, okay? What will be the impact of having stable quantum computers for analog signal synthesis?
Sorry, could you repeat that, please?
Yes, yes. What will be the impact of having stable quantum computers for analog signal synthesis?
As far as I'm aware, absolutely nothing, because this is most likely a task better suited for classical computing. Even if we did have stable and fast quantum computers, there is no computational benefit, as far as I'm aware, to actually running any sort of digital audio processing through quantum computing. That's mostly, as far as I'm aware at least, useful for sort of statistical purposes and improving, time complexity with things like cracking passwords and whatnot. But I am just saying words. That is well outside my domain of expertise.
Okay, perfect. Let's see another question. Can you use Synchrotron out of the box without writing Python code?
Yes. So it does come with a bunch of built-in nodes. All of the nodes that I used currently are all built in. You can expand it just by writing your own code right into a directory called nodes. And then as long as Python is able to see them, you can expand as much as you want.
Perfect, perfect. Well, another one for you. Can you share the name of that cute little MIDI keyboard?
Yes, of course. This here is the Teenage Engineering OP1 Field. It is meant to be a standalone instrument as well. I'm using this as a MIDI keyboard because it is the most portable MIDI keyboard that I own. It's also the only MIDI keyboard that I own. But yes, it's an OP1 synthesizer.
Thank you. Well, there's other question from the audience.
Thank you. I'm an hobby synthesizer playing too, and I just want to make you congratulations for this, because for your age, it's really amazing, and just congratulations for you.
Thank you so much.
Very, very good work.
Thank you.
Not really a question.
I share a similar sentiment. I've built an audio library myself called Easy Audio. And
yes, I've seen Easy Audio, yeah.
Yeah. So very impressive to see it in Python, because like I come from the world of like C, C++, like the juice kind of audio processing things. So one thing I had a question about, just because like clock time synchronization between nodes, I saw that you had like a global object that you're using there.
Yes.
Is that sort of encapsulate? Let's say I have like in this case we had sort of like single sort of node going into like multiple effects chaining, but if I had like a file player and like I had like 3 nodes, like a multi-track kind of thing, how does Synchrotron deal with that?
So Synchrotron does actually have a node for reading in a WAV file as an input source, and the way that this is handled is that each of these output nodes, these playback nodes, register themselves globally as being a target audio sync. And then the bottleneck just ends up being whichever is the slowest output sync. So for instance, if I have just this here, the bottleneck would be the audio driver, where the audio driver has a callback, where it's after it's played a buffer, it's going to say, I need the next buffer. So it's going to be more or less real time. If I replace this with writing to a WAV file, it will run as fast as it can, as if you're rendering or exporting audio from a digital audio workstation. If you have both, then it will write the WAV file still, but it will only write it as fast as the playback node throttles that.
Interesting. So you could have like an offline rendering sort of node
Yes.
as well.
And if if I use the console here, there is a global clock which keeps track of the current time in number of samples, which is how it keeps everything in sync.
Gotcha. Cool. Great work. Yeah.
Thank you.
Thank you, Andrew.
Thank you so much.
Congratulations. So.